Hello everyone, my name is Christina and I'm a PhD student from the University of Connecticut. Today I'm going to be talking about the sensitivity of a machine learning based model that we have developed to predict chlorophyll-A using multimedia modeling environmental predictors. Before I continue, I would like to acknowledge the people I work with, my advisor Marina Astita, people from the EPA, Valerie Garcia, Shenling Tan, and Jesse Bash. And I would also like to acknowledge Dr. Wanek from the University of Connecticut. The scope of this project is to use multimedia modeling and machine learning to assess algal blooms. In the past at CMAS, we have already presented our machine learning-based methodology using Lake Erie as a case study, in which we integrated modeled and observed data in order to identify and evaluate important environmental parameters and predict chlorophyll-A concentrations, which are a proxy of algal blooms. Today, we will focus on examining the sensitivity of the model when it comes to varying input model data. We will do this through sensitivity tests where we exclude or include certain meteorological, air quality, hydrological, and agricultural data. Our study area is the United States part of Lake Erie, and our study period is from 2002 to 2012. In situ chlorophyll-A measurements, which serve as the observed variable, are provided by the Lake Erie Committee Forage Task Group. These chlorophyll-A measurements are then seasonally averaged from May to September. As presented in the past, we're using modeled or environmental variables, which are provided by various linked and coupled numerical prediction models run at a 12-kilometer grid spacing. We're using weather variables from WRF, atmospheric nitrogen deposition variables from CMAS, fertilizer applications from EPIC, and hydrology variables from VIC. These four models serve as the explanatory variables used to predict the chlorophyll-A observations that are provided by the LEC, and we put all that data into the machine learning model that we built using random forest to predict chlorophyll-A concentrations in the lake. Since last year, we have updated and improved our model by using outputs from updated versions of EPIC, WRF, and VIC. We are expecting to receive new CMAS simulations by the end of the year, but for now we are using an older version of CMAS. This is the complete list of variables that we're using to train the random forest model. In orange are the static variables that indicate the location of the station in the lake. In purple are the weather variables from WRF and a duration variable for air temperature that we have created. In pink are the wet and dry nitrogen deposition variables from CMAS. In blue are the VIC variables and also a duration variable for water temperature. And in green are the EPIC fertilizer application variables, which have been converted to tons. In total, there are three types of variables. So we have the static variables that indicate location, point variables, which are closest to the model grid point to each station in the lake, and watershed variables, which are aggregated by averaging or summing for all the grids in the Huck 8 watershed that drains into the lake. In total, there are 29 variables that are evaluated. The first step in the methodology is to train and validate the random forest model with all the explanatory variables. Step 2 is to examine the performance of the random forest model through tenfold cross-validation and evaluate the importance of the top explanatory variables through accumulated local effect plots. Step 3 is to evaluate the influence of each set of the parameters through sensitivity tests by varying EPIC, VIC, WRF, and CMAS inputs into the random forest model. This slide shows the preliminary results of the prediction of chlorophyll-A. The plot shows the out-of-sample prediction of chlorophyll-A, and you can see that over 65% of the variance in chlorophyll-A measurements is explained by the random forest model, and 94.8% of the model's predictions are within a factor of 2 of the observations. From the contingency table, you can see that eutrophic conditions, which is when chlorophyll-A concentrations are higher than 5 micrograms per liter, are identified 73.7% of the time, and that the model can correctly detect between eutrophic and non-eutrophic conditions 87.5% of the time. This is pretty good performance. However, we do see that higher chlorophyll-A values are underpredicted, and one of the main reasons this is because there are few high chlorophyll-A values in our dataset. The plot in this slide is the variable importance plot, which ranks the 29 explanatory variables that were used to train the random forest model. The variables with higher percent increased MSE are considered of greater importance by the model. We can see that many of the epic fertilizer variables are highly ranked, specifically the application of organic nitrogen and organic phosphorus. We can also see that precipitation at the watershed from WRF is also highly ranked, being number 4, followed by the static variables, longitude and latitude, and VIC and CMAS variables. To study how a specific variable affects chlorophyll-A concentrations, we use accumulated local effect plots, or AOE plots. Here's a simple example about AOE plots using the latitude variable. From the AOE plot on the left, we can see that chlorophyll-A concentrations are highest at the latitudes corresponding to stations 3 and 4 on the map on the right. The random forest model correctly identifies that the most chlorophyll-A problematic locations are located in the west, followed by the central and then the eastern basins of Lake Erie. In case you are wondering, the low point at the beginning of the AOE plot actually corresponds to station 7, which records the lowest chlorophyll-A concentrations. So another example is the precipitation variable, which is at the watershed. And this clearly indicates that an increase in precipitation at the watershed leads to an increase in chlorophyll-A concentrations. This is supported by recent studies that indicate that precipitation and river discharge increases nutrient loads delivered to the lake, which in turn leads to an increase of algae activity. The last thing I wanted to talk about is about the sensitivity of the model. Various sensitivity tests were made by varying the input of variables, but I will only be covering a couple of the most interesting findings due to my time limit. Here on the left, I'm showing you the results of a sensitivity test I did by running only WRF variables into the random forest model. And on the right, I am showing you the results of running WRF variables together with static variables, which indicate location in the lake. So the only difference is that on the right side, we have latitude and longitude. In this sensitivity test, we find that the spatial variables latitude and longitude are significantly important for our random forest model. The run, including the static variables, has a much better R-squared and lower errors. In addition, we see that the run on the right with static variables can predict higher chlorophyll-A values than the run on the left. And it can also predict up to 52.6% of eutrophic conditions compared to the left, which predicts one occasion less of eutrophic occasions. This sensitivity test shows the importance of keeping the spatial variables latitude and longitude in the model. On this slide, I have another comparison. So on the left is the WRF and static variables sensitivity test that was shown on the previous slide, and on the right is a new sensitivity test using only epic and static variables. Overall, the run on the right, which includes fertilizer application variables, performs slightly better in terms of R-squared and has lower errors, But most importantly, the run on the right performs significantly better when it comes to predicting higher chlorophyll-A concentrations. This sensitivity test shows that meteorological variables alone are not enough for predicting high chlorophyll-A values, and that fertilizer application variables are influential for predicting high chlorophyll-A concentrations. This is supported by other studies that indicate that there's a relationship between harmful algal blooms and accelerated eutrophication from human activities, and the effort for the US and Canada to reduce phosphorus loadings over the past decade. Our model has some limitations. There's a lack of high chlorophyll-A observations for the random forest model to train on. There is no lake hydrodynamic information such as lake thermal structure or water motions. It would also benefit if the model had wastewater discharge information coming from industrial and municipal sources. And we also are not taking into account the Canadian portion of Lake Erie, even though we know that US contributes to over 84% of the total phosphorus loads to Lake Erie. To summarize, the model has been improved with updated versions of VIC, WRF, and EPIC. The results are promising, but more quantitative assessment is necessary. The model ranks the 29 explanatory variables conducive to successful prediction of chlorophyll-A, ranking nitrogen and phosphorus fertilizer applications as the highest ranking, followed by location, meteorology, hydrology, and air quality variables. In the future, we plan to expand our study period from 11 years to 16 years, expanding up to 2017 once we get new CMAS simulations. We will also be trying different machine learning approaches, and given sufficient record of data, the predictive tool can be applied to lakes and coastal locations to study other water quality indicators. The goal of this project is to be able to build a predictive tool capable of providing water quality forecasts. Here is the list of references that I cited throughout the presentation. Finally, I would like to give a special thanks to Jesse Bash for providing the new EPIC and WRF simulations, Shelling Tan for running new VIC simulations, and Valerie Garcia and Marina Estita for the constant guidance and support. We would also like to thank James and Patrick from the Lake Erie Forge Task Group for providing valuable information and guidance on how to utilize the LEC data. And we have the EPA disclaimer here, and thank you for watching.